Okay, let's get started. Welcome back to Engineering Geology and Soil Mechanics. Today, we are going to discuss about the phase relationships and the soil compactions. Last week, we've discussed about origin of soils and grain size distribution and plasticities and the atomic limits. And all things considered, we are able to classify our soils, coarse grain, fine grains. In the coarse grain, we can see the grain size distributions. And then for the fine grain soils, by using hydrometer analysis, we can reclassify. And then according to the soil classification standard from USA, from British, we can name it. For example, soil, sand with the polygrade sand, and then well-graded, something like that. This is our soils and the fundamental classifications. And then we should get a move on the next topic, the phase relationships, which make us to describe our soil in a scientific manner. So after today's lectures, you're able to know how to sketch and then label the various components of soil in a phase diagrams. And then how you are able to know how to calculate the following the components: void ratio and porosity, degree of saturation, and water content, and unit weights. We need to describe our soil in a mathematical form. That's why we have to understand each terminologies. Soils are composed of solid, like a soil particles, liquid, like a water, and gas, like air. The solid phase may be minerals and organic matters, and the spaces between the soil particles are called void. We have voids. Probably this void can be filled with fluid and gas. The water in void called pore water. This pore water play a crucial role in the behavior of soil under certain load. Let's say all the voids are filled by water. This soil probably fully saturated. If let's say this void is filled by water and air, this soil is probably unsaturated, partially saturated. Let's say all voids are filled with air, no more water. This soil is said to be dry. So this total void volume equals to air volume plus water volumes. As we can see, this is the nature of the soil. Need to get it simplified. This phase diagram can represent the components of soils like soil particles, air, and waters. Without any external loads, the total volume should be constant, while the volume of pore air for water varies between 0 to the maximum volume, total void volume. These relative proportions of each phase affect the soil's physical properties. Let's say the water dried out. It would be dry soils. And let's say air has gone due to the water being fully filled. Every void, it will be saturated soils. It means that the mechanical behavior between saturated and dry soil is totally different. That's why the void, this pore space is important, and the agent, water, air in the pore also very important for the soil's engineering behaviors. This is the completely dry soils. There are only two phases, solid and air. Water in the void was already dried out. The voids include the purely air. Therefore, the void volume equals to air volume. Make sense? This is a fully saturated soil. It is also has two phases, solid soil particles and water. These voids are fully filled with water. In this case, void volume equals to water volume. All nature of soils are unsaturated conditions, partially saturated conditions, being composed of soil, particles, or water, or air. In this case, we have three phases. So I guess so far you guys are with me right now. Let's focus on. I need to quantify the relative proportions of solid, water, and air in the soils, which is the scientific effort to describe the soil behavior in terms of mechanical behavior and hydraulic behavior. A lot of terminologies, but we have three total categories: volume related ratio, mass related ratios, and density related ratios. These volume related ratios terminologies or mathematical formula are made up of quantities related to volume, V. Soil volume, water volume, void volume, and total volume. Mass ratio, so all mathematical formulas are made up of quantities related to mass. Total mass, soil mass, water mass, air mass. Can you feel any weight of the air? Normally 0. And then mass to volume ratio, which is the density. So we are going to deal with soil density. Ensure that the density of air is assumed to be 0. And then density of water is taken as 1,000 kilogram per cubic meters. 1 gram per cubic centimeters. Okay? Very common sense. This is the typical phase diagram of soils. Total volume, total mass. Soil volume, soil mass. Void volume, void mass. Water volume, air volume, water mass. You don't need to memorize. Yes, prof, I don't memorize this because this is understandable. Yes. After 10 minutes, I will ask again. So from now on, I will be explaining the important definitions and corresponding formulas to describe the proportion of each component of the soils. Let me walk you through. First, I will deal with the volume related definitions. All equations are made up of volumes. First definitions, void ratios, which is the ratio of volume of void to the volume of solid. The VA plus VW is the void volume divided by total volume, soil volume. It quantifies the void volume against soil volume. And porosity is similar, but a bit different. It is the ratio of the volume of voids to the total volume. It ranged from 0 to 100%. Can be represented by percentage. It exhibits the void volumes against total volumes. What is the physical meanings? The bigger the void ratio and porosity, the larger the void space is, right? My finger is the soil particles and they mixed up. Now we have a lot of space. I can see you between the voids. It meaning very loose conditions. And after some compactions, something like that, we will get, now I cannot see you. We will get smaller void ratio and porosity compared to initial void ratio and porosity. These quantities tell us about the void spaces proportions. And then third things in the volume ratios is the degree of saturations, which is the ratio of the volume of water to volume of void. We are not talking about air. We only consider water in the void. So we want to figure out the amount of water in the soils technically in the void spaces. It is usually expressed as a percentage. So S or SR equals to 1 or 100%, the soil is considered as fully saturated. And this degree of saturation S equals to 0, the soil is fully dry. Now let's move on to mass related ratio. Mass meaning we can weigh it, right? Water content is the ratio of mass of water to mass of soil. It is usually expressed as a percentage. Just say soil has the 0 water content, the soil is in the dry conditions. The water content should be less than 100%. Can it be equal or exceed 100%? mostly impossible. So let's say we have a certain soils, and then we can weight soil first, and then we can also measure our container mass. Then put it in the oven, wait again. We can get soil mass, dry soils plus water mass. Hi, Pro, what is the difference between water content and degree of saturations? I just said to you, water content is the mass. Degree of saturation is the volume. Okay? But the physical meaning is quite similar. Next, density or unit weight. Soil particle density. Our soil density, particle only, is the mass of the soil particle per unit volume of the particles. We only consider volume of soil and mass of soils. And when you consider here gravities, the density becomes weight, right? Yes. 9.81, roughly 10. And then we have a very interesting terminology, specific gravity here, GS. Specific gravities, which is the ratio of the soil particle density to the water densities. It varies between 2.2 to 2.8. Yes, when you calculating soil particle densities, mostly you can take the dry soils. And the specific gravities, it is quite easy. You can prepare some water in a certain carriers, and then you can put something on the water and soak into the waters. Let's say this something objects soaked and then settled in the waters. That object is heavier than water, right? It means that your specific gravity is greater than 1. And then you prepare another one and then put it in the waters. And then this object float on the waters. This specific gravity is still lower than 1. For examples, sand. You just stepped out and then take some soil sample from your playground and then some out there, and then you can put it in the waters. All soil particles settled down, right? Sedimented. It means that soil particle heavier than waters. How much? 2.2 times and 2.8 times. This is the specific gravities. When you hear about specific gravity, oh, these objects need to be compared with water. All right? Yes, we have a lot of density and unit weights. Bulk density and total density. This is expressed by total mass per total volume. We don't care about how much water, air are present in the soils. Our only concern is total mass versus total volume of the soils. The total density depends on the degree of saturation because total mass will change due to changes in water. So if the degree of saturation becomes 100%, the density is the saturated density. Because saturated density also defined by the ratio of total mass to total volume. Certain soil specimens is fully saturated, the total density becomes saturated density. You take soil samples, oh, high probe. This is the partially saturated. Yes, most of the natural soil in nature is partially saturated. Looks also partially saturated. So you can weigh total mass and total volume. You will get total density. What about the dry density? Take the soil samples. And then 24 hours, no rains. And even daytime, very hot. So the soil fully dried. Looks like the soil came from oven. Take the soil sample, the specimen's mass and volume. Of course, it is total mass, but considered as fully dried. It means this mass only for soil mass. Technically, we express mass of soil, but generally we consider as which is total mass. Make sure that soil particle density is the dry soil versus only volume of soils. This is quite similar, right? This is the dry conditions. But the expression is different. So now I'm asking you, can you memorize all the terminologies and the simple equations? Cannot. Yeah, of course you can memorize, but I don't recommend. Understanding each concepts and simulates in your head, in your brain, makes you very specialists in the soil mechanics. Because after these modules, you're going to attend geotechnical engineering module and foundation engineering modules. Can you memorize all the things 1 year, 2 years? Cannot. But if you try to understand what it is, 1 year after, 2 years after, you can still apply this concept into your problems. Okay? Let's think about the effective density and we can so-called submerged unit weight. Submerged unit weight. The effective density rho prime is used in the calculating the effective stress below the water tables. I just mentioned to you effective stress, meaning soil particle here, they are contacted each other and only consider soil particles, the stresses acting on the contact surface. So, which is the saturate unit weight density minus water. This is a fully saturated soils. And then take out water effect. This is the submerged unit weight. Please do not confuse between density and weight. Weight means mass times gravity. Unit weight is the weight of soil per unit volume. So because soil weight is relevant to both the loading and resistance of soils, quite useful to consider the weight per unit volume of soils. Because mass times gravity considered as force. Force meaning we have certain mass and certain directions, right? Gravity is the gravitational directions. So normally we say unit weights as a gamma is density times gravity, rho g. This is our unit weight. Typically, our sand soils, the unit weight ranges from 17 to 23, and clay is 11 to 21. These are the typical ranges of the soils. Now, we discussed three categories: volume ratio, mass ratio, and density. For the volume ratio, void ratio, porosity, and degree of saturations. Mass ratio, only one thing, water contents. And density. Density is the volume over mass. Sorry, mass over volume. Dry, saturate, and partially saturate. Right? So, based on these, the fundamental definitions, there are many types of relationships among the basic conditions, basic definitions. Okay, let's remember the water content is the mass of water per mass of soils. MW over M, what? S. This is the typo, right? Total density, rho is total mass per total volume. From this, let's start with total density. This total mass can be decomposed into the mass of solid and water, something like that. And this, the numerator can be sorted by MS. And then MW over MS is water contents. So simply the total density can be expressed by these equations. The terms water content, dry density. It is found that if we have the dry density and water content, we can calculate total density. And then let's say we have total density and take the soil sample, high probe, partially saturated. Yes, this is quite natural. And then we know about total density here. And then we also obtained water content by using these procedures, right? It means that we know total density and water contents. Yes, we are able to calculate dry density. Sometimes dry density, dry unit weight is important because this is the indicator to check whether some sort of soil compaction conducted very well or not. Okay? Yes. So we can convert it to unit weight. Total unit weight is dry unit weight plus 1 plus water content. Then we also have interesting relationships. The void ratio and porosity can be defined as these equations, right? The VV over VS total V, right? This relationship between these two things, we can convert it to from void ratio to porosity. Quite simple. And then we also have degree of saturations. Can be expressed by volume of water divided by volume of void. Amount of water in the soil void. And then let's see, based on the void ratio definitions, we can express like this. The VV equals to void ratio VS. And then VS, VW can be represented by each the density terms. And then we remove the duplicated water density. And then we get these relationships. Okay, better to memorize. SE equals to WGS. S, degree of saturations. E is the void ratio. W is the water contents. GS is specific gravities of soils. SE equals to WGS. SE, WGS. Speak. SE, WGS. 3 times loudly. SE, WGS. SE equals to WGS. SE equals to WGS. From the dry unit weight definitions, it can be expressed by weight of soil over total volume. Each term can be break into the specific terminologies, and we can get GS gamma W over 1 plus void ratios. It means that dry unit weight also can obtain from certain void ratio and yes, void ratio, because GS is mostly constant and water unit weight also constant. One is the digit value, only the things varied is void ratios. It means that if you know the void ratio, you can simply get dry unit weight. Hi, Pro, how to calculate the void ratio? Of course, we have a specific methodologies and then in laboratory, but we have alternatives. You see here, by using SE, WGS, these terms derive to this. So if you know water contents and degree of saturations, we also get dry unit weight. Let's see these phase diagrams. Same soil volume, void volume, soil mass, water mass, air mass equals to 0. Starting with a unit volume of soil here. Just assume. Hi, Prof. I want to assume total volume equals to 1. Yes, you can. But right now, we assume the soil volume is equals to 1. Considering our void ratio definitions, the void volume equals to void ratio. And then based on our degree of saturation definitions, water volume equals to SE. Because VV is E, the water volume is SE, right? So let's take a look at the mass. Mass of soils is Vs rho S, which is the soil particle density, right? Rho S equals to Ms over Vs or Rs, right? So Vs rho S. And then this Vs equals to 1, right? And then rho S Gs times water density. This is the specific gravity definition, right? Because Vs equals to 1. So Gs is water density, soil particle density over water density. That's why the how it the object heavy or light, something like that. And then MW is VW rho W, right? VW equals to SE here. SE rho W. SE equals to WGS. WGS rho W. We can change their terminologies and definitions into different form by using the fundamental definitions. Why? Why do we need to change and then derive the different form of the equations and formulas? Because every situations we will have different given conditions. Sometimes contractor just gave me water contents. Sometimes contractor gave me degree of saturations. Sometimes contractor gave me nothing. So only what I can do is just take the soil sample volume and mass only. In this case, we can simply derive the certain sort of equations, and then we can infer specific quantities. That's why we learn about the void ratio, volume ratio, mass ratio, and then density related the equations. And then we can assume the soil volume equals to 1, and then we derive certain formulas. Hi, Pro. In reality, soil volume is not one. For example, 21 cubic meter. Wow, 21 cubic meters. What you can do? Times 21, 21, 21, or 21. Here is the examples.